Let's begin. Okay, so function y is implicitly defined by y cubed minus 2y equals 3x squared minus 4x. What is true about this function at the point 1, 1? Y is increasing and concave up. Y is increasing and concave down. Y is decreasing and concave up. Y is decreasing and concave down. The concavity of y cannot be determined. All right. Well, again, let's talk about what are we looking for? Are there key words that we can see here? So the first keyword I see is implicitly. So we have implicit functions. Now, once we see that, we're thinking, okay, so this will probably be an implicit derivative. So when we're taking an implicit derivative, we say, how do we think about y? We say, well, y is a function of x. What function of x is it? We don't know, but we say, like, well, let's pretend like we knew. And then we can take derivatives. So we're going to take derivatives. Now, we did notice somebody else said, hey, we see things like increasing, decreasing. When you see increasing, decreasing, where do you look for that type of information? Yeah, so this here is telling us we want to look at our y prime at the point 1, 1. What about concave up, concave down? What is that telling us? Yeah, that's second derivative information. And here we're trying to say, let's look at y double prime at 1, 1. So increasing, what does that tell us about y prime? Or what is y? How do we know if something's increasing? Y prime positive, function increasing. So y prime negative, function is decreasing. Okay, concavity. Y double prime positive means concave up. Y double prime negative, concave down. So this really is a question on, hey, what's going on with the sign of the derivative and the second derivative? All right, so a plan. Do implicit differentiation, plug in the point 1, 1, and look at the sign of the first derivative. And then keep going, do a second round of differentiation, plug in, look at the sign of the second derivative. So that's our plan. All right, with all that said, A, B, C, D, or E. What was the answer? B as in boy? All right, good. It is increasing and concave down. So our plan, we're thinking of y as a function of x, take a derivative. So y cubed depends on x, so we have to do chain rule. So you have 3y squared times the derivative of y, which we're marking here by the derivative of y, minus 2y prime, and then we're taking the derivative with respect to x, so the other side is 6x minus 4. Well, we're going to need second derivative, so take another derivative. Now here, 3y squared times y prime, what rule will you need to take the derivative of 3y squared times y prime? So I can rephrase it. What rule will you need to take the derivative of the product of 3y squared and y prime? Product rule. Know your rules. So the derivative of the first, 3y squared, gets you a 6y y prime times the second, so y prime again. Then the first, 3y squared, derivative of the second, that's the y double prime. The rest of it is very straightforward. Now plug in 1, 1, you get y prime equals 2. So we know we're positive, we're going up. At 1, 1, we know y prime equals 2, so you can plug in the 2. And we also know that y equals 1, so we can plug those values in. We get y double prime is negative 18, concave down. All right, fun problem. Any questions? Cool. All right, nice warm up. Now we can start getting into some real good challenging ones, right? No, it won't be that bad. All right, number 2. Find the derivative of f inverse of x. And then this notation means at x equals 5. And we don't have f. In fact, we don't know very much. We just have a table. Now, when we see a table, they're really testing us not on the procedures, they're testing us on the formulas. Do we know the formulas? Now, is f inverse of x just x? No. Boy, that would be nice, because then the answer would be really quick. It'd be 1. It's very tempting. They like to put tempting answers here. They're very good at tempting us. Okay, so we can't just say, it's like the derivative of x. We have to work a little bit harder. So we're going to be tested on the derivative of the inverse. What else will we need to know to take this derivative? Chain rule. So this is derivative of the inverse and chain rule. Now, how do we know it involves the derivative of an inverse? Because we see an inverse. And so we need to know our formulas. So let's see if we can remember our formulas. So, according to just generic, the derivative, I'll use g inverse of x, is 1 over g prime of g inverse of x. Okay, good. That's our formula. So we're basically, this question is testing you on this formula. All right, so we have answers: 1/2, 2/3, 1 4/3, 3/2. The answer is 1/2 is right. Good. So we need to use our chain rule. So be careful here, because it's easy to lose what's on the inside and what's on the outside if you're not paying attention. So this layer, f inverse of x, that's our inside. And that corresponds to this f inverse of x here. So it's 1 over f prime f inverse of the inside times the derivative of f inverse, which is 1 over f prime f inverse of x. Okay. Now we have to figure some things out. Well, we know we're plugging in 5. So we're going to have to figure out what is f inverse of 5. They haven't given you a row for f inverse. So how do you find f inverse of 5? What do you do? So f inverse of 5 is the same as asking the question, f of what gives you 5? So if you're looking for f inverse of 5, scan the row for 5. I see a 5. And I say, okay, what was the corresponding x value? It was 1. So f inverse of 5 is 1. Well, we're also going to have to do f inverse of f inverse, right? So I also need to know what is f inverse of 1. So I scan for 1. I say, there's a 1. So f inverse of 1 is 7. All right. So now we plug in. So we plug in 5 into our derivative, and we just start working our way from the inside out. We know what f inverse of 5 is, so we get 1. We know what f inverse of 1 is, we get 7. So it's 1 over f prime of 7 times 1 over f prime of 1. So we grab those two, multiply them together, and flip them over to get 1/2. All right. That's number 2. Any questions? Okay, cool. Number 3. Given that h of x is equal to f of x g of x, and the following information. So we have information about the value of f and g, of f prime and g prime, and f double prime and g double prime at 2. And the question, determine which of the following statements is true about h of x at x equals 2. So we have 4 statements, 5 statements. One is saying, h2 is not a critical point. The other ones are, it's a critical point, but it's a max or a min depending upon what happens with our second order derivative. All right, so what's our game plan here? What are we going to be using? Yeah, we're going to take product rule, take a derivative, make sure it's equal to 0, take a second derivative, being very careful, and plug in. Now, are all of these answers possible answers? If not, which ones can be eliminated? So if you think about this, what's being tested here, this is testing us on our second derivative test. So it's like, hey, do you know how to apply, that's not how you spell knowledge. Testing on understanding, I can probably spell understanding. There we go, understanding of second derivative test. So, second derivative test, if you're positive, you look like that. If you're negative, you look like that. And if you're 0, you don't know. So, can I be a local max and have a second derivative that's positive? No. So, anybody who guessed C, that was a wasted guess, because that's just impossible by second derivative test. Can anything else be ruled out? What? D. Can I be a local min and have the second derivative be negative? No. So you can, knowing about the second derivative, get to a 1 in 3 chance, and I'm willing to bet you it's not A. So now it's 50-50. All right, B or E? What do you think? E. E as in elephant? Yes. Good. So, we are doing what we talked about. We take the derivative, and then we take the second derivative. You just have to be patient. No surprises. Make sure you don't lose any terms. But the second derivative, that's f double prime times g plus 2f prime g prime plus f g double prime. And we evaluate. When you plug in 2, you get 6 minus 6, which is 0. 2 is a critical point. All right, good. So that's how we rule out A. Plug in 2 into our second derivative, and we're going to get minus 24 plus 36 minus 5, which is positive. Positive means min. So it's a local min, since our first derivative is 0 and our second derivative is positive. All right. Any questions? Okay, good. How are you doing so far? It's like, yeah, haven't gotten me yet, Steve. Well, give me a chance. I'll try to throw 1 or 2 at you. Okay, number 4. This one had a typo. This is the corrected one. So if you're wondering like, there was a typo, like, yes, I apologize. All right, so you're taking the derivative of e to the 3x times x squared plus 1, divide by the cubed root of x times arctangent of x, and we're telling you that the derivative is the original function times some other thing, where the other thing is one of these options. Okay, well, what are things that we're testing you on? What are things we're not trying to test you on? Maybe we'll start with that. What are we not trying to test you on? We are not trying to test you on quotient rule. We are not trying to test you on product rule. And you're probably like, are you sure you're not testing us on that? Well, there's a few things. One thing we're trying to test you on is arctangent, because who doesn't love a good arctangent? That's something that was new since the last exam. But what else? When you see a lot of stuff going on like this, what's the technique? Logarithmic differentiation. So this is testing us on our logarithmic differentiation. Now, can you do it without logarithmic differentiation? Yes. Would you want to? No. Why not? Because you'd make mistakes. Not because I don't think you're great. I just know how bad it gets. And I don't want you to have terrible situations. And the goal of logarithmic differentiation is to make things simpler. So what's logarithmic differentiation? It says if you want to take the derivative of a function, no matter what function it is, it's the original function times the derivative of the log of your function. See here, this is our f of x, and then there's our f of x again. So we're trying to take the derivative of f of x. We're told it's f of x. So that says, oh, that means we're trying to take the derivative of the log of terms. Now, why logarithmic differentiation? Well, you need to know a few things. Let's just remind ourselves. If you're taking the derivative of a log of a function, g of x, how do you do that? What's the procedure? Write a fraction. What goes downstairs?
G of x squared plus 1.
Ooh. Oh, you're doing one of my favorite functions, but it's not the log function. So log just says put in g of x downstairs. What goes upstairs? G prime. And every time you encounter a log, that's how you take a derivative. However, before you do that, you say, no, log, I've heard some pretty cool things about log. What are some cool things? Log of a times b. Log a plus log b. So multiplication, you can separate. What about log of a divided by b? Log a minus log b. So division, you can separate. What about log of a to a power b? B log a. So powers can come down. All of these are ways that you simplify things. So the goal of logarithmic differentiation is when you have lots of things which are multiplying, dividing things upstairs, take the log, and that says everything pulls apart into easier bite-sized pieces. All right, so we know where we're going. A, B, C, D, or E. What's the answer? D. Okay, so as we already talked about, we're taking the derivative. We just take it term by term. Log of e to the 3x gets us 3x. Because log of e to the 3x comes out, log of e is 1. Now, even just here, you say, what's the derivative of 3x? It's 3. That rules out b and c. Okay, then we have log of x squared plus 1. Well, take the derivative of log of x squared plus 1. What do you have? Yeah, downstairs x squared plus 1, upstairs 2x. Well, that rules out a. So now we're already down to just d or e. X to 1/3 downstairs becomes minus 1/3 log x. We can bring that power 1/3 out in front. Derivative of log x, 1 over x. So we should have a 1/3 times 1 over x. Well, that rolls that one out, and now we don't have to keep going, but we will. Log of arctangent. Arctangent goes downstairs. Derivative of arctangent, 1 over 1 plus x squared, which we can put that 1 over 1 plus x squared down there. So this works out. All right. Cool. Number 5. Use linearization at x equals 3 for the function f of x equals the square root of x cubed minus 2 to estimate f inverse of 5.27. Okay. Some key words here. Linearization, that's a key word. When you see linearization, what do you think? You think line, good, because it starts with the word line. And you say, what's our favorite line? Tangent line. So linearization says you're going after the tangent line. So the problem is telling you what to do. It says, I'm finding the tangent line at x equals 3. And now, what's the idea? The tangent line, this is an approximation for the function. That's what linearization says. So the tangent line in general would be f of x is approximately f of a plus f prime of a times x minus a. This is just generic. So we find our tangent line. Now, notice it's asking for f inverse. Are we taking the derivative of f inverse? No. So don't try to pull out derivative of inverses. So even though, you don't want to get to the point where it's like, oh, if I see an inverse, I automatically start pulling out that rule. It's like, no, make sure you know context. So it's saying we're trying to figure out what f inverse of 5.27 is. Well, that's the same as saying we want the output to be 5.27. So where would the 5.27 be going? The x or to the f of x? It would be going into the output. So we're putting 5.27 is approximately, in our case, since it's 3, f of 3 plus f prime of 3 times x minus 3. And then we want to solve for x. So that's the goal. That's the idea. Now, one other question. Currently, f of x is the square root of x cubed minus 2. This is not calculus friendly to write it this way. What's the calculus friendly way to write it? X cubed minus 2 to the 1/2. Because that, when I say calculus friendly, I mean in terms of our rules that we have for taking derivatives. All right, so what's our plan? We're going to figure out what f of 3 is, figure out what f prime of 3 is, solve for x. So we have options, A, B, C, D, or E. Survey says D, 3.1. All right, so here's the work. You plug in. When you plug in 3, you get the square root of 27 minus 2, which is the square root of 25, which is 5. The derivative of 3 turns out to be 27 over 10, also known as 27 over 10. Not much you can do about that one. And so we say, okay, great. So 5.27 is about 5. 27 is about 2.7 times x minus 3. We can subtract 5. 0.27 is about 2.7 times x minus 3. That means x minus 3 needs to be 0.1. So x needs to be 3.1. All right. Any questions? Well, that leaves us one more multiple choice. Okay. So, the function h of x is x to the 2/3 divided by x squared plus 2x plus 3 is continuous for the interval from -2 to 1. That's a statement. That's not asking us to prove it. It's just saying it's true. When finding the absolute max and min of h of x over this interval from -2 to 1, which of the following points does not need to be checked? Okay, so what's our setting? Is there anything that we should be thinking about? Like, what are some words here that are like, I remember this?
Absolute maximum.
Okay, absolute max and min. It's like, hey, we talked about that. Now, absolute max and min, what was the idea? That was we're making a list. We're checking it twice. We're going to find out which points are nice. What goes on the list? Okay, so what are critical points? So there were 3 types of critical points. So what are the 3 categories? So someone said 0. I'm going to say, okay, that's where the derivative is 0. What else? Derivative is undefined. What else? Endpoints. So we are making our list. And as we make our list, we're going to get a bunch of points. Now, you can always test more points, but you don't have to test them unless they make this list. Because the absolute max or absolute min for a continuous function on a closed bounded interval has to happen at one of those points. And it says, well, here are 5 points. one of them didn't make the list. Which one didn't make the list? So what are we going to do? We're going to figure out our endpoints. We're going to figure out where our derivative is undefined, where our derivative is 0, and we're going to compare our list to this list. And whichever one of these doesn't make our list, that's our answer. So we have -2, -3/2, -1, 0, and 1. Which one did not make the list? C? But isn't -3/2 the weird looking one? Just because it's weird looking doesn't mean it didn't make the list. C is the correct answer. Good. Good. Don't be tempted. You know, critical points don't always have to happen at whole numbers. Sometimes you have instructors who are like, aha, we're gonna sneak in a half and see if you're paying attention. So pay attention. All right, so endpoints are freebies. So that's how you know for sure -2 and 1. You can just say, look, definitely not those two. And without a lot of work, I think you can convince yourself that 0 is just going to be an issue right away because of that 0 to the 2/3. That's a very suspicious power. So you can basically say, okay, 0 is going to be an issue, which gives you a 50-50 shot on this type of problem. So even if you can't get it, you can oftentimes reason answers and get it down to 2 or 3 options. That's better than just guessing 1 out of 5. 1 out of 2, you've got a better shot of getting points. All right, so what do? Take the derivative. What rule do you need to take this derivative? Well, you kind of see it there. It's the quotient rule. Do we expect you to know quotient rule? Yes. Oh, that was very unenthusiastic. Yes, I guess. I can understand that. I'm not the biggest fan of the quotient rule, but all right. So we know we take our derivative, and then it's just a matter of being very careful. Factor out what's in common. Whenever you have x to weird powers, you pull out x to the smallest power. So the smallest power is -1/3. And then you just have to keep track of what power is left. So you grabbed all of the x here. I had x to 2/3, pulled out x to -1/3. What's left? X to the 1. All right, so pull it out, clean it up, look for factoring. And if you don't want to do all the work, you can say, look, all I have to do is check these points. So if you don't want to do all of the simplifying, you can say, let me save myself some work. Throw in 0. Does anything bad happen when you throw in 0? Well, yeah. Get 0 to a negative exponent. Bad. That's 0 downstairs. Throw in -1. And you see what happens. And if -1 is a number that's non-zero, then you're like, oh, that's it. I'm done. So even if you can't do all the simplifying, you can just go ahead and plug in and check. So that's one of the things about multiple choice. Oftentimes we have to do a multiple choice problem the same as we do a long answer problem. But you don't. You just have to get enough to determine what is not the right answers. Or you have to get a way that you can check which one is the right answer. So you can often be much faster. All right, so that's number 6. Any questions on our last multiple choice problem? Okay, in that case, we're off to the long answers. And they shall be long. So, number 7. We have the function f of x, which is 4 times x squared plus x plus 2 times e to the negative x over 2. And we're asked to do a couple of things. Find the intervals for which f of x is increasing and for which f of x is decreasing. Okay, so when we're after increasing, decreasing, where do we look? First derivative, f prime positive equals increasing. F prime negative equals decreasing. So part A says take a derivative and look at the signs. We're going to see the signs, and it's going to open up our eyes when we see those signs. Part B is asking about concave up, concave down. What are we looking for? Second derivative. Where it's positive, concave up. Where it's negative, concave down. And then part C says, okay, find and classify the critical points and list inflection points. So where do we look for critical points? We can use the first derivative. And this is looking like it's going to be a pretty straightforward function. So we're essentially saying, look for where the first derivative is 0. How do you classify critical points? What test? Well, you have two options. You have first derivative test. First derivative test, what do? You look at what's happening on either side, right? If I see going up and going down, that says, oh, I'm at a max. If I see down and going up, I'm at a min. So you can use increasing, decreasing on both sides to figure out what's happening for the point. But that's one way. What's the other way? You can do the second derivative test, which says, since we've already computed the second derivative, it's just as fast. So notice it doesn't say which method you have to do. Now, inflection points. How do you find inflection points? Second derivative is 0 and, well, undefined, and what needs to be true? So just because the second derivative is 0, are you an inflection point? No. What has to be true? Well, you have to check what's happening on either side. You have to change concavity. Inflection point means changing concavity. So you have to check. Does your concavity change? So this is a concavity change. All right, well, so what's our plan? We're going to take the first derivative, take the second derivative, clean them up, and we're going to look at the signs. Okay, so this one's probably a little bit on the longer side, which is maybe not realistic for an exam, but it is realistic for a practice exam. So we take the first derivative, and it turns out to be minus 2 times x squared minus 3x e to the minus x over 2. Take the second derivative, clean it up, x squared minus 7x plus 6 e to the negative x over 2. Now, very fortunately, and by really, this was not just a coincidence, we tried hundreds of combinations so that we could get both the derivative and the second derivative to factor. So we found some nice pairs. So the first derivative factors x minus 3. There's a minus 2 e to the minus x over 2. So we say, aha, critical points are at 0 and 3. Draw your number line. Mark 0 and 3. And test. So how do you test? You plug in. So you plug in any number bigger than 3. What number do you pick bigger than 3? Trick question, any number. But yeah, you pick a simple number, right? Don't be like, I'm going to try the square root of 17. No, 4. Make it easy on yourself. Remember, we love ourselves. And so we're going to give ourselves easy numbers to work with. A quick note, what's true about e to something? The exponential functions. What's always true about exponential functions? They're always positive. They're super optimistic. They're always looking on the positive side of life. Okay, so anyways, we test the intervals. We see we're negative, positive, negative, which means we're increasing from 0 to 3, decreasing from negative infinity to 0, increasing from 3 to infinity. Don't stress about your inequality signs. There are people who will insist it's one kind of less than, and other people will say it's less than equal. Don't worry, we don't test on that. But we do test to make sure you have the right points. All right, similar thing happens for a second derivative. Now it factors into x minus 1 times x minus 6. You check your signs again. And you get similar things about concavity. So your concavity changes. All right, so finally, part C. We have critical points at 0 and 3. If we do the first derivative test, we see 0 is a min, 3 is a max. If we do the second derivative test, we find out that 0 is a min and 3 is a max. Is it surprising that they gave the same answers? No. They will give consistent answers. Now, sometimes the second derivative test is inconclusive, but if they both say min or max, they will both say the same thing. And then we do see that, in fact, the sign does change, which means that both 1 and 6 are inflection points. All right. So, good. In the interest of time, any questions? Okay. So, number 8. G of x is 1 plus arctangent of x minus 1 to the power of 3x plus 1. We're asked, find the linearization, use the answer to estimate. Okay, so a couple of things. First off, we see linearization. What does that tell us? Tangent line. The key for linearization is there's a line. So, okay, so we're doing tangent line. We've already talked about linearization, so we won't repeat. So we need to find the tangent line here. Now, what do you notice about this function? Other than you probably don't want to take a derivative. You will have to take a derivative. But what do you notice about it? How are you going to take this derivative? You are forced to do something. You're going to have to use logarithmic differentiation. There's no choice. You are forced to do logarithmic differentiation. Why are you forced? Because you see an x downstairs and you see an x upstairs. When you see an x in both places, there's no choice. Logarithmic differentiation is the way to go. So, we're testing on logarithmic differentiation and linearization. After we've done part A, where we found the tangent line, how do we do part B? What's the punchline? The tangent line approximates the function, so plug in 1.05 into the tangent line. All right, so I don't want to belabor that because we've done logarithmic differentiation before. So you work through it. It's not as bad as it looks. It's mostly a lot of writing. So just be patient. Don't rush. Take your time. Once you have your function in the derivative, evaluate. You get that your value of your function is 1. The value of your derivative is 4. So your line looks like 1 plus 4 times x minus 1. So this is the answer for A. Then you plug in for B. Plug in 1.05. Becomes 1 plus 4 times 0.05, so you get 1.2. All right. I want to get to our word problems, because these are the ones that people love. At 12 noon, there's a train that departs Central City and heads due west at a speed of 20 miles per hour. Simultaneously, there's a train heading due north towards Central City at a speed of 30 miles per hour that will arrive at 4:20 p.m. At what time will the rate of change for the distance between the two trains be 0? Okay, what type of problem is it, and how do we know? Related rates. Why is it related rates? Because they're giving us rates, right? Here's a rate, 20 miles per hour. Here's a rate, 30 miles per hour. Is there any other rates? Rate of change between the two trains. They give us 3 rates are involved. How quickly one train is moving west, how quickly one train is heading north, how quickly the distance between the trains is. So we have 3 rates. They're related. Now, when you see related rates, they basically fall into a few very basic categories. They are Pythagorean theorem. Should we list the categories? Yes. Related rates. You have, not related rats, related rates. You have Pythagorean. Now, when do you apply Pythagorean? That's when you have the sides of the triangle are changing. You can have similar triangles. This is often when you talk about shadows. Who knows what evil lurks in the hearts of calculus problems? The shadow knows. Sorry, it's an old-time radio show. Ask your great-great-grandparents. Okay. We also have geometry problems. So things like spheres, cones, cylinders, they tend to be popular. Like you have a sphere blowing up and like, okay, what's happening? You can also have some trig involved. So what's an example of a trig problem? Well, we did the rocket problem, right? Where there was a rocket that was launching. So imagine that's a rocket. And then you were a viewer. You're like, hey, what's happening to this angle? Now, if you see a trig problem, how do you do trig problems? What do you need to remember about your trig? SOHCAHTOA, yes! And what do? Well, you say, well, which of the two sides do I know anything about? So, for the rocket, you know how far you are, and you're interested in how fast the rocket is going. So what's the right trig function? What relates opposite and adjacent? Tangent. So then you say, there's a tangent theta that's going to drive the relationship for the related rates. But it might not be that. It might be the opposite side and the hypotenuse, or it could be the adjacent side and the hypotenuse. So think about if you have an angle involved, SOHCAHTOA that problem. But more or less, that's it. You know, we're not very creative. They fall into these types of categories. Now here, we have a train heading west. We have a train heading north. And we have the distance between them. And we care about the distances here. There's no angles involved. What category are we? Pythagorean. All right, so. Did anybody find the answer to this one? What time? Because this one is fun, because it didn't say a distance, it said a time. So did you find the time? What was it? It was 3 p.m. Okay, so we have our a squared plus b squared plus c, a squared plus b squared equals c squared. And we say, okay, those are our three distances. They're all changing. Take the derivative, 2a dA dt, 2b dB dt equals 2c dc dt. All the 2's cancel. The dc dt needs to be 0. We know how fast the trains are going. So A is increasing, so it's plus 20. B is decreasing, so it's minus 30. So you get 20A minus 30B equals 0. That says 2A equals 3B. But you can say, well, how big are A and B? So you can figure it out. Starting at noon and going for t hours, A is at 20t, and B is at 130 minus 30t. And if you solve for t, you get t equals 3. So at 3 p.m., the distance between the two trains is exactly changing at a rate of 0. All right, let's talk about the last one for a minute or two. You run a bakery, and you have one final cake to make for the day. And you check your pantry and see that you have plenty of everything except frosting. But frosting, everybody looks, that's the first thing they see. That has low supply. Now your bakery's signature frosting technique uses 3 times as much frosting on the top of the cake as it does on the side. and you're going to follow the common practice of not frosting the bottom side. Given that your cake will be in the shape of a cylinder, and that needs to have exactly 81 pi inches cubed of volume, what should be the dimensions in terms of radius and height to minimize the amount of frosting you'll need? Okay, so what kind of problem are we in? And how do we know? Optimization. How do we know? We're trying to minimize something, and there's lots of words. If you have lots of words where you're trying to minimize or maximize something, you're in optimization. Now, what about this part here, this 81 pi? What is that? So that's a constraint. So it's saying you can't just have any arbitrary combination of the radius of your cake and the height of your cake. You have to have combinations that give you a specific amount of cake. You have an order to fulfill. They have hungry people. You need to give them the right amount of cake. All right, so when you're doing optimization, what do you do? What's our procedure? When in doubt, draw a picture and start thinking about, okay, we need some frosting on the top. We need a little bit of frosting on the side. So, and we have our constraint. So, all right. In the interest of time, did anyone come up with the dimensions? How tall is this cake? I'll give you a hint. It's a whole number.
6.
Give you a hint. It's a nice number. 9. Yes, it's a cake of height 9. Radius is 3. In some sense, you probably can guess the answer, but we don't care so much that you guess the right answer. We care that you do the right process. So we're trying to minimize frosting. We say, well, the top of the cake, you need pi r squared. You need 3 times as much as the side. So 3 times the area of the top plus the area of the side. So the side is the circumference of the circle is 2 pi r times the height. So we are minimizing this expression, given pi r squared h equals 81 pi. Use the relationship to knock out a variable. Replace h in terms of r. So we get down to a single variable, take the derivative, set it to 0, solve, and in this case, there's only one answer. That must be it. So that's how we get our answer for radius of 3, height of 9. If they ask you to verify it's a max or min, what do you do? Either second derivative or first derivative test. Be ready to pull it out. All right, that's it. Good luck on the test.